go.
It is now recording and it's getting my audio.
Now if we walk around, it should be able to hear. Yeah.
That'd be ideal.
Welcome to ENA Exam Review.
Do we want to turn the transcript
Am I doing virtual?
No, I like it on so that way I can make sure it's still reading and they can hear us.
Good point. Welcome to ENA Exam Review, all four of you guys, or if you're listening online, all right? So I didn't put this in the presentation because low-key I made this at 3 a.m. But I do want to give some pointers for anyone who's in this class. This is what got me and Fern through the class, all right? So if you're doing it on your own, obviously review all the stuff that's in this PowerPoint and in your exam. Sebastian's making a gesture, a doy gesture at me, but I want to put that in there. But what got Fern and I through is we got the fundamentals down. We like the laws that govern the circuits. And then we got the way of like analyzing them. And then we just did like 20 problems. It was a couple of us, and we just, for like 3 hours on a whiteboard, we just write circuits down and go through the motions, solving them individually. So if you want help with that, or if you've already been doing that, great, but that's really how you get the most prepared for it. So that's to all of you guys. I'll keep it personal. That's what I do. Yes. I'm just gonna do a bunch of problems.
So you're sick of them. Then do more.
Oh, it's funny. I blew on this because anyway. Okay, so we're gonna go over a couple of these. Wait, okay. How many of what do y'all need the most help on?
Probably like mesh nodal.
Mesh,
yeah, maybe
after.
Let's spend most of the time, I think, on mesh nodal, and what do you guys think?
And that one, they would be like 7 minutes.
Op-amps are pretty easy. Everyone thinks they're hard. They're pretty easy, and I'll give you an example. And then we'll do some Thevenin and Norton. I don't know about energy storage elements. That's capacitors and inductors, right?
Yeah, so they will
Okay.
be on there, but it's just like general
You could also talk about maximum power transfer as well.
maximum power drivers gonna be there.
Okay, I'm gonna need to look that up because it's not on the PowerPoint, but I'd love to do that.
Via evidence necessary for our parking lots.
Yes, that's right. I remember doing that. You remember doing that? I remember doing that. Okay. So this is some background information. Stop me if there any of these give you questions. But yeah. Voltage is the what? Electric field times distance. Yeah, thanks. I'm getting a nod from my other ENA guy. Current is the change in charge over change in time. So it's like a flow of water. Voltage is like the water pressure, basically. The one thing I want you to take away from this is passive sign convention. Okay, this is what gets a lot of people confused. If you pick a direction in a circuit, you have to stick with it the whole time. What did I do?
You're making it vertical.
Oh, my bad.
Hey, Lon, I'll drop those pellets.
That's $100.
Oh my gosh.
Yeah.
Can I turn off the rotation?
Your screen recording.
There it is.
Now you're good.
All right. Nobody saw that. Perfect. So passive sign convention. You pick a direction in your circuit, you gotta stick with it. And so I actually do this a little differently than the diagram on the PowerPoint, but it's as long as you stick consistently what's on there. So we have ourselves like a little baby circuit.
You can also zoom in if you need to, like pinch.
Yes, I will. You know, think about the direction that your current is going. And then even if it's wrong, like, even if it's conventionally like weird, like one of these currents, these blue lines could be like -4, right? And then that means it's actually going like in that direction.
That's
right? But the idea is pick a direction and make sure you're sticking to that direction and things should work out. Does that make sense?
They just along the branch or?
Yeah,
Everything.
along a branch, what we're mainly thinking about is, yeah, like resistors along a branch, like for instance,
Like all that.
you've got VA and VB. If you're talking about current this way, it would be VB minus VA over R, right? But if you're doing it this way, it would be VA minus VB over R. I don't know why I capitalized one, the other one not. But whatever the real actual current is, you'll get it. Let's say the actual current is going this way, which means therefore that voltage A is higher than voltage B, right? Well, that just means that this would be a negative number, right? Just keep that in mind. It's simple at its base, but it gets really confusing if you let it get confusing. But yeah, just stick to your guns on that one. It just makes you really consistent. So yeah, sources. I don't know if I need to be super like detailed about this. Did your professor give y'all the like, oh, is this feasible thing or like 5-3?
For us.
Did y'all get that?
Yeah, he likes conceptual a lot, so like, this is gonna be work problems. Can you do this in like,
Can you,
Theory or no?
can this ideally exist, Kevin?
Yeah, it's just not smart.
I mean, in like ideally.
Yes.
Cause it doesn't obey Kirchhoff's voltage law. These ideal sources, how is this 5 volts? This is.
I suppose if
something
they're just gonna be on their own, then no, but
Yes,
I'd like.
you could do it, it just wouldn't be smart, you're right, the voltage would be across the other ones and then it would have like a huge current because there's no.
Yeah, it blow up.
It would blow up.
We don't worry about this. What about this? Have you all learned about this? So this is a voltage source. Let's take the IV curve. Which one's the x-axis again?
the one on the horizontal.
Voltage.
Voltage, yeah, that's right, thank you. I do this all the time, and yet. Let's say, so this is a voltage source, which means no matter what the current is, it's the same voltage no matter what, right? Well, that slope is equal to, what is that, change in Y over change in X, or V in this case. There's infinite change there. There's no change in the voltage, so it's basically approaching infinity. Well, in this case, R is equal to V over I. I had to do that real quick. Or 1 over infinity. Conceptually, voltage sources have no resistance. Does that make sense? Again, right? Does that make sense following the IV curve?
Yeah,
Okay. It's reverse of the slope. Well, let's look at a current source. Let's take a little gander here. No matter what the voltage is, current's the same, right? The slope is 0. Well, as we learned, R is equal to V over I, or 1 over the slope. So it means it's approaching infinity. So current sources have infinite. Did y'all gotten to the point where it's like Thevenin and Norton circuits and you get rid of the sources? This is why current sources, when we get rid of them, they're open, and voltage sources are shorts.
Oh,
Because you can think of them that way. Does that make sense?
I know, yeah.
Right?
That makes so much more sense.
Well, yeah, I did a pretty good job with that, I think. Yeah, okay, Kirchhoff's laws, I think y'all get this one. Water pressure, until you get to magnetism, this actually doesn't exist, but we don't talk about that. And then this, I mean, it makes sense. You can't, where's the extra current going or where's the current coming from? It all has to come from somewhere.
what goes in must come out.
Exactly. So we're gonna keep going. All right, resistor series in parallel. So I wanted to derive this for you, but I think I forgot. So I'm just gonna be real. But everyone knows, y'all know how to add resistors in series and in parallel.
Yes.
I don't think Kevin knows how to add resistors. He looks a little panicked.
I remember 50B derived it. I just forgot what he did.
That's the thing. But it's not, as long as you remember, it's pretty simple.
Yeah.
It's,
Did it right?
I'm pretty sure if we were, yeah. Well, like, so y'all mind if I try?
Yeah, just go for it. Let's give it a shot.
So the I is the same, right?
Yes.
But it's V1, V2, V3.
Let's do our, oh my God, I was thinking like 10 minutes. Because I was doing it by hand, right? So I also prepared it by hand. So I'm gonna come with it. Yeah, but like, I.
Or. So in series, oh, that was actually really easy.
Oh, yeah. I see, just back out the eye. Yeah, that makes sense.
You do not need that.
Yes.
This is like.
Oh, yeah.
Right?
Yeah.
Oh my gosh, we're gonna get even crazier. Let's say we've got like a thing here.
Resistors in parallel.
Yes, what is that? That's V is the same. So that's IT is equal to I1 plus I2 plus I3. I equals V over R. V total, V is the same across all of these, right? So. In this case. So it's already the reciprocal, but I is equal to V over R, which means 1 over that R total is equal to 1 over blah, 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 blah. A lot of writing there. So, yeah, so if you forget, God forbid, it's not super hard to derive. Just remember they come from Kirchoff's laws. So just remember what's the same. That also helps if you kind of forget how voltage dividers work, which I did on every ENA exam I took. So read that on the tutor. So how did y'all do delta to Y in your class? This man did. Did you? Okay, so here's the thing.
I did also.
This is hard to solve. I'm gonna put. Hard to solve.
Yeah,
Yeah.
It's not easy. Because how do you do like if you've got this thing, or I think it's actually. No, that's pretty hard to, that's pretty easy to solve actually. Or is it this? One of these is hard to solve. I forget which one.
yeah.
But basically, we try to collapse resistor networks a lot. And depending on where these are both in the circuit, it can be really hard to collapse. Just because it's like you have to see parallel or series, and sometimes they're not planar, which means there's like overlapping resistors or so. This is a tool to help solve that. And I'm not going to go into too much detail. I would say before the exam, just take a look at this and remember the formulas. But to convert one way, to go from delta to Y, it's essentially the other two resistors. You see how R1 is RB and RC on the top?
You can use a laser pointer too.
Can I use that one?
Laser pointer right here.
No way. That's crazy. You see how R1 is RB and RC right here? It's the other two that are not the one that it's connected to normally. It's kind of like the opposite two. And then you divide by the full resistance of like the delta. There's a way to convert back from Y to delta, but I don't quite remember it. Just know that these two structures between each other are super useful if you're trying to collapse the resistor network. And you don't really want to use node voltage analysis. This is a good alternative. So yeah, oh my gosh, that's so cool.
Right.
Okay, voltage divider. So this is what we just did, basically. The I is the same, right? Well, you do a bunch of fancy work with this. Anyone struggle with the concept of voltage division in this group? I don't know whether or not to speak to people who will be watching this or to y'all, by the way.
Well, do
What should I do?
both for general, you know?
Both for general?
Yeah, just
Okay.
it's like some people would.
I'm not necessarily gonna,
But if they do talk, we can hear them, right?
oh, other people? I think it's
I don't think so.
just, yeah, it's just y'all. This is so intimate. It's great. I've always wanted to be intimate.
This is recorded.
That's right.
This will be on YouTube.
This is going on YouTube?
Yeah.
I'll keep it family
We
friendly.
can edit it out, I think.
I don't know. This is the real me, you know? This is the real
No, I
me.
respect it.
It's me and
This is what you
the.
get.
Keep it real.
That's true. This is the Gordon you get when you show up in person.
True.
Okay, so yeah. V1 is equal to, so the higher the resistor. the way I remember this is not actually mathematically, but it's conceptual. So let's say that R1 is huge, much bigger than R2. Well, voltage is the pressure essentially dropped off on it, right? So you've got this big resistor minus a small one. In terms of actual like area, it would actually be smaller because resistances. But anyway, we don't worry about that. Well, your voltage across this is going to be much bigger than that one, right? So that's what this expresses. Voltage across 1 is the resistance of 1 over the total. So if the resistance 1 is huge, like basically infinitely times bigger than R2, well then this would go away and V1 would just be V times R1 over basically R1. V1 would be equal to the total voltage, right? It's in a way, I don't want to get too confusing, but it's like that's what wires are. Wires have infinitesimal resistance, right? So we can estimate that the actual resistors are taking up all the voltage.
Okay.
Is that, I don't know.
Yeah, that makes sense.
Okay,
Yeah, it's like.
I'm not throwing y'all off too much.
Wire.
So like with voltage dividers, all you have to do is just like divide the resistance that you want, divide by the sum of all of them, and then multiply by the total voltage.
Yes. Yeah,
What if there are three or more resistors?
if there are 3 resistors and you just do this exact thing, so VI is equal to V total times RI over R total.
Okay, that makes sense.
That's the big
That's
general
the
term.
Gotcha.
Yes. And then let's see if I remember this correctly. Trying to think about what current dividers are before we get there. But this is the specifically 2-form divider, which shows up a little bit less, but it's still important to know. Current's the opposite of voltage. In this specific case, not like in all cases. But if you've got a big resistor here and a small resistor here, which one is the electricity going to want to flow into more?
Smaller.
Right? Yeah. So if R1 is greater than R2, then the IR1 is going to be much smaller than IR2 because it's going to allow more current through. So you can see it reflective in this, where I across R1 is equal to the other resistor over the total, which means the bigger your resistor is, the bigger R1 is, the smaller the actual value is going to be for I1, right? But if R2 is bigger, then the current across I1 is going to grow. So it's an interesting thing. Do y'all do cheat sheets? Is y'all on cheat sheets on your
We
exam?
get open notes.
Okay, yeah, keep this on. The electric properties, especially in ENA, it's kind of when you're starting to cement it. So a lot of these relationships are going to be a little confusing, but give it a couple of months. Like Vern and I we had to fight to remember, but then by the end of the year, it was like, yeah. So
One thing I will say also, this equation for current division only works if you have 2 resistors.
yeah,
If you have any more than that, because of like, since you add them up inversely, it doesn't work out.
that's a really good point.
To be in parallel.
Yes, so current, yeah. Whereas voltage division is in series, current division is in parallel. Yes, and that's true. If you were to do more, you would just use KCl and it wouldn't be super hard to find it. I believe there's also a general current division for more than 2 resistors in parallel out there.
is, but it's kind of.
It's kind of, it's a lot on the brain to think about. So, all right. Oh,
Really, if you want to simplify it the most, just find the current across a branch where the resistors you care about are. That way you can do current and voltage division, if you just focus on the branch. In series, the branch is a circle, in parallel, there are multiple branches.
interesting. Yeah.
That's right.
Yeah. How are we feeling so far?
Pretty
So
good.
who knows better than
Okay,
you?
that's all, that's the light stuff.
That's the basic.
In terms of, so those relationships, I'm sure, are sitting kind of loosely in your heads, still like, what's going on? The ENA gives y'all some really nice tools, basically. So my favorite one is not mesh current, but we're gonna go through both of them just so that we can get a good idea of what to do. So no voltage analysis is no more than a problem-solving method and it's like Sudoku. It's, if you give yourself the time and think about it, it's pretty rewarding. So yeah, all you do, you identify all the nodes, and we'll go over what nodes are. You select one of those nodes to be ground, which means no matter what, that's our 0, and everything else is referenced from ground. We write Kcl equations, and we convert it to the voltage difference over R, which is right here. Again, this is very general stuff. We'll go over the steps because I have an example problem in just a second. And then we solve it. It's just like, our teacher was always like, yeah, just do the algebra and you're done. And it's the most time intensive part, but it's not hard. Right, look at this, guys. I've got a problem for us. Let me see.
You have to use node voltage analysis.
How do I change the color?
Yeah.
I see 2 nodes. Have you guys seen?
On most problems, when they just.
I see 5 nodes.
When
What?
they just ask you to find whatever on one point, you have these.
Yes, so normally one of these exam problems would be like, find this current or find this thing. We're just gonna solve this whole thing, all right? We're just gonna get the whole thing done. So any point, let me see, between components, right? Where it's where 2 or more branches connect. Yes, okay, so this is a node right here. This is a node right here. This is a node. Any point where it's in between those things, or the technical definition is where 2 branches intersect. So you can think of these 2 as 2 branches. Obviously, you can smash some of these together and make it easier for yourself, which we will be doing. But that's just to keep that in mind.
Definitions of node versus branch.
Yes. Yes.
I thought that would, the one that's right, that's not in there. I thought it's just whenever you have like more than 2 branches.
More than.
I believe it's 2 or more.
I mean, technically, so
Yeah.
the rules still apply because current going into the wire and out of the wire needs to be the same. But you don't do that usually because they're in series, right? So the current's gonna be the same.
Okay.
When it's a
Yeah.
branch, the
Just
current's
like-
gonna
just like-
split, that's when it's hard.
So you can do either way. I like doing at any point between because then there's no room for error. So right here, it's pretty easy to tell what it is, but we'll go over it. So I'm just gonna dot all the points in between. That's a big one. So I'm gonna name this A, I'm gonna name this B, C, D, and then we're gonna ground this one, which means we just define E to be 0, right? Well, we define E to be 0. What's A? What's this one right here? Does that make sense? Yeah. We've got VA, spell volts, man, y'all are already geniuses.
Okay, nice.
Does that make sense?
Yeah.
Between the power? Well, we've got another one. Looking at this source, what is voltage at node D? You go from 0 and you add 6. Super simple, yeah. And it's, it's not as complicated as it looks. If you look at this circuit, it's like, wow, that's a lot. But yeah, sometimes it's just like, go up. These sources are from voltage. You literally just add what it is. Especially if it's across one branch like this. It's.
So what direction is that going? It's just going up.
Oh, that's very good, Allison. Let's do that. Huh? It's like what color I want. Yeah, so I'm just gonna start like doing what I want. And again, you could do all of these backwards if you want. But this is the way I see it. I picture this as current flowing in here. And then current flowing down. Does that make sense?
Yeah.
Together? Is that? Okay. All right, so the next thing we're gonna do is, so that was step 1. And we did step 2. We identified all the essential nodes. We chose one of them to be ground. Now we're gonna write the KCl equations for all the other nodes. So we need VB and VC, right? Let me see. So for VB, KCl and VB, we have current flowing in, and then I'm writing it as current flowing out, and then current flowing out. That's gonna be VA, or let's actually do, let's say that's, I don't want to get too confused. Here's what I'll do. The current flowing in is that VA minus VB, right? We're gonna divide that by the resistance, which is 100 ohms. Does that make sense?
Yeah.
Current flowing in, okay. And then we're gonna say that's equal to the current flowing out, which is firstly VB minus VC over 300. And then we're gonna add, let's see, VB minus ground, which is 0, right? 0 over 200.
Yeah.
So VA minus VB over 100. I'm gonna zoom in a bit so that I'm not taking up all this space. Man, I have no clue how my professor did this. It's crazy. VB minus VC over 300 plus VB over 200. Now we have VA. Yeah, we have VA, right? So our first equation has two unknowns, and it's VB and VC, and we can get VB in terms of VC if we do a little fancy algebra, right? But before we do that fancy algebra, I'm gonna get that second equation. We need voltage at C, right? Stop me if this is not making sense. Does it make sense?
Yes.
Okay, good. I never know the difference in like knowledge, and a lot of this is just new, which is what makes it so confusing. Yeah, VC should be much easier actually, because the current going in is the current going out. Let's see. Oh, whoa. Oh my gosh, it doesn't keep going. So VB minus VC over 300 is equal to VC minus VD, but we know that VD is 6 volts, right?
Right.
Bam. Over, what is that, 100 ohms? Yes. So now we have two terms, two independent algebraic equations that connect VB and VC. Now, do you want me to solve it through, or do you think you can get it from there?
I think you got it. I think the hardest part is driving the equations, but like,
Yeah.
we all know how to do algebra.
Yeah, that's true. Although I always got mad at my teacher because he was like, just do a little algebra and you'll get to the answer. This will take you the longest time
Yeah, that's
Well,
out of
what I've
anything.
always heard is that, we get to this point, you can do all this crazy you can quote unquote do all this crazy calculus and circuits, and then you get to algebra, simple arithmetic, it's like,
Yeah.
that's the hard part, that's where you mess up.
That's the thing. Y'all get to a point where it's like, yeah, it's the damped frequency response, the double derivative of, and then you get to the algebra and you're like, I don't want to do this.
You have to put it in a matrix.
I'm gonna put,
You don't have to.
you can do this.
Our professors are using plug into a calculator. They're like MATLAB.
Yeah, you can't put it, at the end of the day, it's a system of equations, so the easiest way to do it would be.
We've been doing this
matrix.
since middle
Yeah,
school.
honestly, yeah.
That's how I did it.
Example
If you just wanna do
continued.
it As a regular system of
No,
equation,
ain't.
that's
there.
perfectly fine, you do you. I would strongly recommend doing a matrix.
Yeah.
Now we're gonna do something totally different.
Right?
Mesh current analysis. This is the goated one.
Oh, yeah.
I'm just kidding.
My favorite.
It's whichever
This
one you
guy.
want to do. Personally, I like this one because it gets complicated resistor networks to be kind of easy. Like you don't have to use delta to Y if you really know how to use node voltage or mesh current, and mesh current's my jam. No.
Yeah, it's just Wi-Fi. Just talk.
Yeah, that's
There
true.
we go.
Okay. So mesh current analysis, it's the same thing. but instead of nodes, we're gonna identify our meshes. Oh my gosh, did I?
It looks like the same.
Maybe the same.
Might be the same.
Yeah, because you don't need a reference node.
Yeah.
It's actually current.
Yes.
First node.
It's identify meshes. Then we use KVL around them. This one is great. It rewards you pretty well, but definites, keep in mind, no, be very careful about your mesh current. This is where passive sign convention is really annoying, but also rewarding, because if you pay very close attention to what direction it's going in, it works out. But you get one thing wrong, the whole system of equations is thrown off. So, what? Don't worry about this. There we go. Allison, you're supposed to check. It was good. I can't believe this.
It looks pretty nice to me.
Oh, good.
It was at 12 a.m. though.
Yeah. Okay, so it's already got our meshes laid out. Additionally, you can do super meshes. You can also do super nodes, where it just goes all the way around. We don't talk about that. All right, we don't worry about that. You can if you want to, and that works if there are per se like weird dependent sources. Like if there was a big dependent source right in the middle and you wanted to just ignore it, you actually can. And then that ignores your dependent source, basically. It makes it much easier. But that's something that I just never really did because it gets a little confusing. But yeah, so we've got our I1, and notice that they're all going in the same direction. Well, what we start with is we do our KVL. So we've got our meshes. We're going to do our KVL across. So I always like listing it out on my paper.
Are we just trying to find each of the currents?
Yeah, we're just trying to, in this case, there's no specific answer to this circuit, but there will be on your exam. This is just how to generally solve one of these. This is how you can get like every voltage and current value and resistor value.
Yeah, pretty much just by finding those currents, you can then just use Ohm's law to find the remaining voltages or whatever I'm asking for.
Oh, you know what? We don't need KVL I1.
Yeah, it's just, yeah.
I1 is equal to 2. Does that make sense to y'all?
Yeah, well, I mean, I still KVL, it's just.
Yes. I1 is equal to 2 amps. Right there. So let's start at I2 then. KVL at I2. I'm going to start on this side. So V is equal to IR. And we're going to follow each of the arrows. So in this case, for voltage, I'm going to do voltage in green. I'm going to call it plus, minus, plus, minus, plus, minus. All right. So let's start this off. Plus 2 times I2 plus 4 times, and then this is where it gets interesting. Because it's not just I2 on that 4 ohm voltage. Oh, you know what? It's also not, hold on. Okay, wait. Let's restart. We have 2 ohms. The current across that resistor is, as you can see, not just I2 going this way, but I1 going that way, right? So 2 is the resistance times the current. Current is I2 minus I1. Right? Does that make sense to y'all?
Yeah.
Perfect. Plus 4, we're going to do it again. I2 minus I4. That's that resistor right here. Then plus 3, I2 minus I3. Now, if we fill all these in fact, I'm going to just off to the side put I3 is equal to negative 4 amps. Does everyone see why I did negative 4? Right here?
Yeah. Yes.
No, it's because against the 4. That's the sign.
It's just a passive sign convention. Once
Yeah.
again, look at that. See, big brain. You gotta use that big brain. Let me see. Let's fill this in real quick and see what unknowns we actually have. 2i2 minus 2 plus 4i2 minus i4 plus 3i2 plus 4. And that, because it's going around the loop, we're doing KVL around the loop, that equals 0. Well, look, that's one equation, two unknowns. That's I2 and I4, right? Now let's do the second one. Let's look at I4. I'm going to start with that 1 ohm. 1 ohm times I4. You see how that's, oh, you know what? And we can't forget. Always make sure you know what direction you're going in and think about that. Solid thing. That's 1 times I4. Now look, we're starting with the minus when we're going in that direction, right? So it's going to be minus 4 volts and then plus 2I4. And then, because we're keeping on that voltage, we're starting with the minus. That's minus 4 for the 4 ohm resistor times I4 minus I2. Does that make sense? Everyone getting that? Okay, yeah, these are always intensive, but look at that. Now we have 2 equations. We have 2 equations with 2 unknowns. Y'all think you could be able to solve these on your own?
Yes.
Plug and chug,
Yeah.
substitution.
Plug and chug or substitution.
Yeah.
Or just move them around until the numbers make sense. That's what I always do. Yeah, sweet. All right, let's keep going then. Let me see. Check. All right, this is what I wanted to get to, all right? Do y'all understand superposition?
Yes.
Heard it,
When you
but-
explain that, like, a voltage source has no resistance, current source, that's what, infinite resistance, that kind of like.
It clicked.
You look-
Okay, so I'm gonna do a little bit for anyone who might be watching online,
That's good.
but there also probably won't be very many people watching online, so I'm gonna be quick with it. But yeah, so y'all saw from the IV curve why we think of them that way.
Yeah.
So for voltage sources, VI R equals 0, or it's approaching 0. Hey guys. For the current source, this R is approaching infinity, which is why we can do that right here. So, yeah, and because circuits are linear, and you're gonna, we talked a little bit about that in linear algebra, but personally, when I was a year behind where you guys are right now, I didn't quite get what linearity meant, but it's just if you increase the voltage or increase the current across the resistor, the voltage or the other component rises with that exact number. The derivative is constant. It's all clean, which means we can
Straight, not-
smack them all together. We can pull the circuits apart, analyze them differently with different sources, and then put them together, and the numbers will add up. So it's very convenient. So I'm going to do a real quick example. How does that look? That looks fun, right? That's enjoyable.
Terrifying.
Yeah, imagine doing that solely like node voltage or mesh current without taking those sources apart. That would be a real silly move if you ask me. We're trying to find I of X right here, right? Well, what we could do instead is we could remove that current source. And X.
No fun, no shame. We love you, Gordon.
Thank you. We'll get you some Russian. That is not a lie. The world knows.
Oh, no.
And they're gonna find out eventually.
Well, what's that? That's just. Does that make sense what I did?
Yeah.
Remove the current source? That's just, let's see.
Have to just remove the.
It's the ones with the, it's on your pinky. Yeah, so
Wow.
and then you put it as the,
Yeah. So the thing is, we're solving for Ix, which is right here, but this is Ix of only the voltage source, right?
Right.
So we can we can get rid of the current source. This is not the full circuit. So when you do this, it's not the full answer. But we're gonna get an Ix of V if we do that. And I'm confident that y'all can solve this circuit. Are y'all confident that you can solve this circuit?
Yeah, it looks great, yeah.
combine their series, then combine
And then
them.
some
Yeah.
resistors there.
Yeah.
And then we can get rid of the voltage source. And I'm gonna actually use my second slide for this one.
Yeah.
That's negative 3 amps. Oh my goodness. That's just,
Yes.
Let's just do that.
I'm not a big fan of negative numbers. I'm a real positive guy, you know? Thank you, Jason. 2, 4, 3, 1. 2, 4, 3, 1. And then this is just. Oh, is it? Wait.
Yeah, because that middle branch is a whole.
Yeah,
node.
there it is.
You can just expand you could just punch that down, like one Ix across the middle, couldn't you? Like keep them in parallel, but combine those little wires.
So like an H.
Yeah, like an H.
Oh,
But I feel like that.
you're
makes-
so right. Oh,
This look, I think this is easier to visualize. what's
We're
around.
parallel and series,
Then
so that
if
we
you
can.
do an
Yeah,
H.
that's an Ix. So
But I feel like this is a little harder to visualize. What's it parallel, at least for me,
which this,
So it'd
When
be
it's like this versus-
condensing it
earlier.
on
when you
RDT.
had- It's the same.
so what's harder to visualize?
What's in parallel and what's in series.
Yes,
When you
so
can't combine it.
this is where, so this circuit is a little difficult. I'm gonna say. I really, it's like out of 3 stars of difficulty, this is like 1.5.
Yeah, it's on rating.
Scared of the
Asterisks.
Yeah, what 3 stars be? Something.
3 stars, ooh, you don't wanna know 3 stars. So what I would do, this is a tough one. I wouldn't do any fancy tricks. I would just do mesh current or node voltage. And if you pay very close attention to each of the nodes or each of the meshes, it will get you that Ix. And if you want, we could do this one if you feel like you're a little, or if anyone feels like they're a little thrown off by the circuit.
I mean, wouldn't you just, well, cause maybe I'm looking at this wrong, couldn't you just, put the 2 in the.
Sorry, Kevin.
Oh, good.
Apologies.
Couldn't you put those 2 in parallel? Oh, yeah, cause I'm the other guy.
Yes.
You know, you can collapse them both individually in parallel, then.
And the issue is how do you get this across if you collapse them both?
Oh, we're trying to find, okay.
Right?
Yeah.
So you could, and it would give you probably some insight into the voltage differences there, but
It would not be higher.
it would not be Ix. If you want, we've got plenty of time.
Work it out.
yeah, you can do all that.
Now I can show you how I do mesh current.
Let's go.
So firstly, I'm just gonna draw. Anyone a node voltage fan in here? Anyone a node voltage analysis fan? You're built different from me. Do you have a preference?
No, go.
Okay, so yeah, what Sebastian would do, what silly head Sebastian would do, is this is here, because there's no voltage difference across this is all one voltage, right? And then VC is 0. So that's actually a pretty solid node voltage problem. The only issue is I have trouble figuring out in that IB or in that VB like node, what the IX is right there. That's a little confusing. So we're gonna hit it with the mesh current because I feel like that's the best way in this particular case. So IA, can anyone tell me what IA is?
Negative 3 amps.
That's right.
That's right. Pass up that PSV, PSC,
That's
PSC.
the second mention.
Yes, -3 amps. That's one mesh current done, guys. We're so good. Now we're gonna do the KVL at IB. I like using lowercase. I don't know why. I think it's because I'm used to time varying, and a lot of your classes will do time varying things in lowercase and time invariant things in uppercase. You'll notice that when you get to like capacitors and stuff.
But this would be time invariant.
That's true. You know what? For the sake of academic integrity,
Consistency.
academic consistency, right? In fact, you know what? How about we're gonna be bureaucratic about it. As one is. Okay, that way there's no confusion. So at IB, we've got, let me make sure I've got the volts right, 2431. 2431. We have, firstly, IB is going to be equal to negative IX. Does that make sense? So, there we go. So let's say let's zoom in. This is our this is the middle of that circuit. We've put a hypothetical IB here. And we're looking for our actual value, which is biased this way, IX. Y'all see how that's kind of it's the opposite, but it's the same in terms of magnitude. Yeah. Okay. Good. Yeah. You always have to find the connections. That's one of the first parts. But we also across IB have, let's see. Oh, always forget. Don't be like me. Don't forget. No way.
Is it the?
No way. That's good.
It would equal to
ID and
negative
IA
IX.
or two?
Oh, you're right. So
Would you not also be considering ICs when you're finding IX?
yeah, I'm trying to figure out where. Oh, you know what? Oh my goodness gracious.
It's IC minus IB, right?
Yes. Thank you. My bad.
Okay.
X is equal to.
Step it up.
That's my bad. Yeah.
You gotta earn your salary.
Each and every one of y'all are gonna fail the ENA
Yeah,
exam.
bro, like, super
Blame
baller.
Gordon.
He's getting paid in experience.
IB. Wait, what? There's no way. I did this wrong somehow. All right, pop quiz. What did I do wrong? That's what I did wrong. I didn't account for the IA, guys. Why didn't y'all help me out? God.
I said IA, so.
Forget it. Go on.
Be -2.
IB minus IA plus 4 IB is equal to 0.
Yeah.
Perfect. And then for the second loop, it would be -3 IC minus IA plus, what is that? That's wrong. Plus 1 times IC equals 0. Well, if IX is equal to IC minus IB, then we could do IC is equal to IX plus IB. We could plug that into IC here, and we'd have basically two variables. Does that make sense? So from this system of equations, would y'all be confident solving IX from here?
Because IA is 3, right?
Yes.
3, and so
Yeah.
We
find
know
out
what I-
IX and IB.
Yeah.
Okay.
Easiest like.
Yeah, actually, so IA would get you a constant right there. And so we're actually really close to solving it. Y'all want to. But I also know that y'all kind of know about this. Also, are you here for ENA?
Yes.
Perfect. Welcome. We did, let me see, we did node voltage and mesh current, so if you have any questions about it, let me know. We're gonna jump to like source conversion in just a second.
Okay.
What do you feel like you're still figuring out?
All of it.
Okay, perfect.
That's why we have a video.
That's true. Well,
Video?
we're recording it as well. But also I'd be down to help tutor after this as well, if there's, yeah. We have a chance.
Yeah.
Sebastian's also a tutor.
Oh, yeah.
In case multiple people want to.
So yeah, this would be a pretty tough problem to get on an exam. Not because it's conceptually hard, but just because it's a lot of time. So we did this one first, that's our circuit 1. We found our IXV. This is our IX in current, or for the current source, right? So we could do IX, IS, right? So when we smash these circuits together, all of the current voltage values add up. And then our IX total, what we're looking for, would be equal to the IX from the voltage source we found, plus this IX from the current source. So keep that in mind. Yes. Split circuits on it's pretty cool.
Yeah.
Do we want to move on? How do y'all feel about it? We'll come back to this. We'll go back. By the way, actually, I'll ask. Yes, so this is Thevenin, but more specifically, it's source transformations. That's the fancy word. So you can switch between these using V equals IR. I know y'all know how to do that. But the way our professor taught us to think about this is every circuit, no matter how big or complicated or how small, you can plop into a black box. In that black box, if you test it, is going to have a certain REQ, is going to have a certain V open circuit. See. And then it's going to have a certain I short circuit. Now this is the part, at least for me, that was the most confusing about ENA, because it's a little tough to get. But basically, engineers all around the world don't want to have to deal with these huge, complex circuit things. And so when they put it into a box, they give it like, this is what the equivalent resistance is. These are the certain properties. And then you and I, when we are equipped with this knowledge, can like figure out all the detailed stuff from it. So we'll get to voltage, we'll get to Thevenin and Norton in just a second. But I also wanted to just give a quick example over source conversion. So just remember, V in parallel to an R can be moved to V in series with an R can be moved to I in parallel with an R. My bad. Yeah, y'all are gonna fail this. So in this case, I is equal to what? It's Ohm's law here.
E over R.
Yeah.
Makes a little.
So you have a 10-volt source and a 5 ohm resistor connected to anything. I cannot stress enough. This box could be connected to anything. We can convert it to I equals E over R, a 2 amp source in conjunction with the same resistance, just in a different spot. Does that make sense? Things are clicking, things are happening,
Makes sense.
all right? Yeah, and it's a little unfamiliar, this without an example, so I have for y'all, look how complicated and annoying that looks, huh?
Yeah,
This
exciting, so.
is,
Mesh analysis.
or, yes, this, you could do both. But let's take a quick look. Now, I said it could be connected to anything, right? So if we redraw this. Well, this right here. There we go. This right here, it's part of the circuit, but you can also separate it. We just learned that circuits are linear, right? So you can break this off and it'll act the same way if you put it back on. So that's 2 amps, that's 6 ohms, and that resistor is in parallel. So what we can do is we can hit him with the V equals IR. That's 12 volts with 6 ohms. It's the same exact thing.
Now we can get by.
It simplifies it. Now you don't have that resistor in parallel. Now you don't have 2 meshes, where before you had 2 meshes all the way around. You can get rid of them and make 1 mesh. Does that make sense?
We
Yes,
also do it for that one with the 1 amp.
we are yes, we can. Good observation. What else? There's one more we can do it with.
That voltage source.
Yes, so
Series.
let's do a little highlighting, boys and girls.
Oh, yeah, that's actually fire.
That we can do, and that we can do,
Yeah.
and that.
Um,
Now, don't get too, there's a reason they teach us to simplify resistor networks one by one. Because if you looked at all of these and was like, we're gonna simplify them all and slap them on the circuit, it could work if you're Albert Einstein. I'm not Albert Einstein. And so I would do that, and I'd get the resistors confused or little things messed up. So I would say, do this one first, redraw the whole circuit. If you have the paper space for it, you probably do. Simplify this one and then redraw the whole circuit and then simplify that one and redraw. So, let me see. So let's do that. Just gonna do 12 volts, 6. And then if we're connecting it with the rest of our circuit, 6 ohms. Just drawing it super small. Oh, you know what?
5 ohm and then.
There's no, that's it. There it is.
Same thing.
Yeah. Now I separated them out right here because I want you to see that while it looks like it's kind of embedded in there, pull it out and it's the same thing. It's a black box and the 2 nodes connect to the rest of it. So, well, let's do that real quick. 1 and 5 is going to go to a voltage source in series with that resistor. We know the resistor is going to be the same. I'm going to put 5 right there. And then V equals IR. So what's the voltage right there?
5 volts.
Does that make sense?
5 times 1.
A lot of this, yeah. As a whole, like the whole circuit looks annoying and complicated, but it's like Sudoku. You have to kind of break it down piece by piece. Let's redraw it again. Now, this is a fun one. You see, 5 volts, 12 volts. And you know what? We're going to smash these 2 together and just call that 12. See. Okay, does that make sense so far? Okay. Now, on the circuit here, that 15 ohm resistor is on the other side, but it doesn't matter on which side we place it. So I'm gonna move it so it looks a little less confusing. Does that make sense what I did? Makes sense? Okay. I am a very visual person, and so I like doing that just to make sure like I can see if I can actually do something with that circuit. So now, 17, A, B. Now, the resistor's on the opposite side. Let me make sure that's correct. Yeah. But the current and the equivalent resistance is going to be the same if we put a black box on it. It's the same if we do this. I believe. Someone want to fact check me on this? Sebastian, is that correct?
Because you just change around the position of the resistor.
Okay. Good. So let's change it up. Let's change it up a little.
Would you wanna, I guess you don't have to flip around the end numbers, would you?
Positive
No.
and negative.
No.
Okay, because if you wanted to find the voltage, actually, I guess it's. No, but if you switch it, then
It's just like
it wouldn't matter.
KVL.
would it?
It's still.
Just, I'm more concerned about if you go through the loop on that side. I know, I guess it's the exact same thing.
That's still the same voltage.
Yeah.
It is. The thing is, inside the circuit, things change. But again, we're looking for what is on the
That's
ends.
funky, that's funky.
Yeah.
I never thought of that.
It is a little funky, isn't it? But as engineers, we don't want to think about what's inside the box. I mean, things get complicated real fast as an electrical engineer. And so we want to know what's going on inside. But this is, if we put a box over it and couldn't see it, this is equivalent in behavior to this. It's not the same in structure, but it's the same in the way it acts. And then we can switch it one more time to get that. So
Think about
I will do it on
KVL loop.
2.
You have the source.
17.
Two,
Voltage across. KVL.
Yeah.
It found nice and
I'm the assistant.
That was something clean.
Y'all be able to solve that right there?
Alternatively, don't you just done a delta Y conversion of the T network thing?
Wait, Corey.
Where?
Voltage divider. It's done delta Y conversion.
Probably, but you know, I'm just teaching the methods. Many of these tools will do the same thing. You could do this, or you could just start with this circuit right here and not do any source conversions and do mesh circuit for node voltage, or you can do delta to Y. It's whatever you think fits best, and then whatever you're most comfortable with. Let's say you get to that exam and you're like, man, I can kill delta to Y. I can do it. Do it, all of them. Unless they tell you to like specifically do power conversion or do, you know what I mean? But if it's like solve the circuit and find this, man, I will do what makes me comfortable. So you did that. So that's it. Many of these tools that we use for like problem solving and tinkering with circuits do the same thing. So Kevin, if you like delta to Y, do delta to Y. He's walking away.
Wait, Corey.
Yes.
That circuit, like the one, like the simplified one.
Which one?
The
Scroll
third one.
down.
Yes. The one down here?
Yeah, you can combine those voltage sources, right? Yeah. It's because they're in series.
Yeah, I think so. In fact,
Yeah.
if we were to, so the danger is if we simplify it, if we're looking for, let's say we're looking for like, let's say we're like looking for this right here. We're looking for I beta. For I beta. Well, now when we simplify it, I beta is gone because we've made it into an equivalent circuit.
Yes.
But what we have done, when we make this equivalent, is we can find more information about the circuit. We could find total resistance we could find. So keep in mind the variables you're looking for, because when you simplify, if you simplify too much, you could get rid of them. It's like the problem we did last time where Kevin was like, we could just make this equivalent. We could have just made it equivalent, but then there would be, you know,
It's in the IX.
then there would be no IX.
Oh, okay, so it depends on the problem.
Yeah, it depends on the process you're doing and what you're looking for. But we're given puzzles and we're given a bunch of different tools to solve those puzzles.
Okay. So this example is just to do the simplification of the circuit. Okay.
Yeah, if this was simplify the circuit to Thevenin and Norton, simplify to,
Gotcha.
you could do this. And on that note,
You could chat method.
thank you. Yes, yeah, imagine doing all Thevenin on your exam.
I would.
No, I do it the hard way.
I'm a source transformation enjoyer, honestly. so-
Are
Oh,
you-
yeah, this is.
there's absolutely
like
no way.
Norton- I think Thevenin sounds cool.
Thevenin sounds way
Thevenin
cooler.
sounds cool.
Thevenin
Imagine
is-
naming your child Thevenin.
Good morning. That's what I should say.
But yes,
That's a clean name.
I would be told, but there's some.
Michael Norton invented Norton and Thevenin.
He-
Michael
yeah.
Thevenin,
Dr. Thevenin.
Dr. Thevenin.
Yeah, this was all actually invented by Dr. Circuit. He
Oh.
made all of this.
Oh.
Michael Circuit.
Dr. Michael Circuit.
Yeah.
So,
Michael.
so,
Same.
so we just learned about power conversion. Yeah, this is all conceptual. You've got a black box. It could be 8 million different things in there. It could be like a bunch of different resistors all doing different things. There's like a crazy amount of things happening in there. Well, what we want to do is we want to just put a lid on it and go, I don't want to look at all the confusing stuff in there. I want to know what's the voltage across it when there's nothing, when the resistance is basically infinite, when there's just air. We want to know what's the current through if I put a wire in between. In fact, let me get colorful with this. Let me get colorful. You guys ready for this?
Yeah.
That's the short circuit current. Look at this iPad. Can I have it?
Or $800, yeah.
$800.
She bought it for $500. And this would only,
Yes, go ahead.
this would only work for resistors. There's like transistors and inductors.
Oh,
That's true. In fact, I should get rid of the capacitor.
That's right.
Yes, so the specific version we're doing with resistance, yes, this only works because resistors are linear with time. However, you're gonna get to a point in the year and then in the coming years where you're learning about impedance, especially impedance in frequency notation, which I don't know how far y'all are. That might sound like complete jargon or like Egyptian hieroglyphics.
But if this had capacitors and inductors, and they just ask you to analyze it at DC.
You could just, if you did DC analysis, you could just short the inductors and open the capacitors, and then, yes, that's what DC, yeah, that's true. Very astute observation. Good job, Kevin. Yeah, there's with circuits that are nonlinear with time, so that's capacitors and inductors, it's a little more tricky, but with resistor networks and with sources, ideal sources and stuff, you can do this pretty easily. So what's the short circuit current? What's the open circuit voltage? And then what is the R equivalent? So the R equivalent, we did superposition of circuits. What we're gonna do is we're gonna bias the thing, and then we're gonna take out the source, and we replace it, like if it's a voltage, we replace it with that open wire. And then if it's a current, we get rid of the wire. Or
Circuit.
we open it for a current source and we short it for a voltage source. Y'all
Yeah,
get it. Yeah, you know what's going on. Y'all know what's going on. Okay, so this too has some very simple steps. Place an open circuit between the terminals, and then you ask yourself, what's the voltage there? You place a wire between the terminals and you say, what's the current there? And then you can, if you have both the voltage and the current, you can find R, Ohm's law, super easy. Or if you want to just do voltage and not do current, you can do that too. Hey guys, There you go. But yeah, you just have to find 2 out of these 3. And then you can use V equals IR to bridge the final gap, basically. So yeah, I have one right here. Look, oh my gosh. Wow. So let's find the Thevenin equivalent. And then I'll show you the Norton equivalent because it's so easy when you have Thevenin. We'll stick 2 terminals right here, terminal A, terminal B. And we're going to try to find the open circuit voltage first. Well, that's pretty easy.
Oh, well, I'm sorry, wouldn't you do it from the resistor, not in front of the resistor?
What do you-
The load resistor right there?
Oh, you're so right. Yes. Sorry. In this case, it's already been drawn for us. Make that little loop I did. So let's give this a shot. All right, and it says -1 amp on that. Guys, I'm just gonna passive sign it tonight.
Negative.
It's plumbing. Yeah, I know, it's a little challenging, so.
7, we're being recorded, okay, so.
You will curse me out if I say another, that's another one.
What's not the more transform? But Crystal Foss.
Right, you're playing a dangerous game.
Oh, sorry.
Sebastian's a man with a lot of pent-up anger.
Towards me and the Fourier transform.
It's not super fun, I understand.
If I say Z transform, you probably wouldn't get into it.
Z-transform, that phrase hurts my soul. Okay. So, guys, notice what is the VAB here? What's it equal to? It's equal to, if we're following Kirchoff's voltage law and we're looking at the like path equivalency, basically, it's just equal to the voltage across these two, or these 2 points right here, right? So we need to find the voltage across this 2 ohm resistor. And because these nodes are the same, it's gonna be equal. Yes.
I just have a quick question. If in between that node right there, so that the one next to the 1 amp, if there was a
This one?
resistor, yeah, between that and A, would there be any voltage drop over the resistor?
If this here.
No. No, between that,
Oh, that's,
would there be a voltage drop? Would that have any voltage drop?
well, that's a very good question. V of this hypothetical resistor with the IR, right? What's the current? If it's open circuit right here, what's the current going through?
Zero.
So no, there'd be no voltage drop. So yes, it's there, but yeah, when there's an open circuit and there's no current, there's no voltage drop.
Wait, so how you got rid of the resistor?
Which others? Oh, you mean the R right here? This R is actually hypothetical.
Oh, that's our equivalent?
That's a load resistor.
That's our load resistor. So that's essentially, that's us saying, this is the black box. Those are the terminals. And they just gave us like, what if you had an R? So it's drawing out what we're trying to do basically.
It's just a place for the voltage to drop.
Yeah,
That's very short.
that R doesn't actually,
This.
Yeah, well, I mean,
it's different. So God, it's hard to think about.
I understand. I got it.
Okay, yeah.
Sure. But also does make sense.
It's like our,
More confused now.
this is our testing R. So basically this problem is telling us to find I naught across any R. And so what we're gonna try to do is we're gonna try to put this into a box and we're gonna try to find what's the VOC, what's the internal resistance, and what's the ISC. We can find that R load across that. So we'll see. Well, we'll get there. I'll show you. Let me see. So in this case, voltage AB. Let me see. This is not necessarily the most fun. Let's try it. I'm gonna do. You'll have to forgive me. ENA, it's been a second. Thank you, thank you. Let me see. Everyone get it so far? Okay. So in this case, this is weird. We're doing KCl here, right? Well, the current going in this way is -1, which means it's going out. But I want to bias downward because I'm silly. VB minus VC over 2 ohms is equal to -1. Does that everyone follow so far the algebra?
Yeah.
Okay, so yeah, VB minus VC is equal to -2, which means that the difference between those two.
That's
-2. Actually, I believe that's it. That's our open circuit voltage.
Couldn't you also mesh it as well? So you could just say
You could.
I2
Yes,
is
negative
equal to
Mhm.
-1 amps, and then you just do 2I2 and then it's done.
Yeah, you could also delta to Y if you want it.
You could also Fourier transform it.
You could also,
Yeah,
you could
we're
Fourier
also-
transform if you want it.
Yeah.
Yes.
You can
Fourier transform.
This is a Fourier transform.
To do the Fourier
We
transform.
could
Yeah,
do
it's
a
like a
delta
puzzle.
Y network.
Yeah, it's like, no, 'cause it's all like a puzzle. You
We
put it
couldn't-
together,
I don't
you
think in
find
this
the Fourier
specific
transform,
case.
you know?
Superposition.
You could, yeah, that's true. You could just place, ghost resistors there.
It just shows.
So
I don't know why you made
do
me.
you have a question with the dependent source, by the way?
Actually, but I could pull one up if you want it.
No, that's making sense.
Just make some
You just do this.
I could make one up. That's true. Okay. VB minus VC equals -2. Well, VB minus VC is our open circuit. Does that make sense so far? Where we are? Okay. Now let's do a little short circuiting. That elevator agrees.
Silly. Little Fourier transform.
What's gonna happen to that 2 ohm resistor when we have a short circuit across? Is there gonna be any current
0.
going through that 2 ohm resistor?
No.
So we can just,
Take it out. Okay.
it's gone. Thank you. So, oh my gosh, guys, it's incredibly easy. What is,
Quick question, sorry to interrupt you. Do you guys know why that resistor just gets taken? Well, you can just take that out.
There's no current going through.
Like, and you can also kind of think of it as resistance. Why do we short it?
yeah, so it shorts it because proportionally, ideal wires have 0 resistance.
No, why didn't we
So why did we short it? Oh,
So, yeah, think of it as a resistance. You have like a 2 ohm resistor and then a 0 ohm resistor in parallel. So if you end up combining those, it's
Oh, it's gonna be.
it's 1 over, it's
So
1 over
let's say,
2
yeah.
plus 1 over 0. 1 over 0 stays infinity. So, 1 over 2 plus infinity is infinity, 1 over infinity is 0. So you end up getting
No current.
a,
Okay, that
you end up
makes
getting a 0 ohm resistor.
yes, and let's think about it physics wise too.
The current I6 is the easiest path, right?
This means it's approaching 0. We're gonna say that because if it's actually 0, we can't really divide by 0, but we're gonna call it like almost 0.
Yeah.
So that's what, yes.
You opened up, I'm sorry, I'm a little lost as to where you are now. Did you open up the amp source and then you shorted the 3-volt source? Or am I fine?
I'm sorry.
We shorted the 2.
Yes, so that we haven't shorted it yet, and
Okay.
I'm showing you all how to short it.
Because if you just left that one open, wouldn't it also just literally not matter anyways? Just forget about it,
Which one?
the one amp, if you just open it. Is are we finding the RL? Or,
Oh, we're not there yet. You mean when we're open circuiting the,
if we're
amp?
trying to find the I of the short circuit, couldn't we just find the Thevenin equivalent, and then just convert it to Norton and then you're done?
you could. You could also find, yeah, no, that's true. I guess I'm gonna do all three.
Yeah.
And then I'll show y'all how we can get to.
It'd just be easier to just do it that way.
That's true, but this is tutoring. So I've gotta show you guys how to.
I'm sorry.
Why aren't you more efficiently solving these for the people who are trying to learn how to do these circuits for you? I love you, Kevin.
Back off, man, it's fine.
Okay,
Sorry to Kevin, by the way.
so let's use a water analogy. You've got a water pipe. And all water's going through here, and you've got a pipe that is, there's none, that there's no water,
Right.
right? Proportionally, that's what's going on here. Right? All the water is gonna go through, the one with less resistance, and there's gonna be none there. Well, that's what's happening here too. All the I is gonna go through here, and so no I is gonna go through here, so we can just get rid of it. It basically doesn't exist. And that's because it's infinitely larger in resistance than that no resistance Y. Is that
Yeah, that's
Okay.
nice.
good? I figured, yeah.
Water makes everything.
Forgive me, I never know when someone gets it or not, so I keep going. Yeah, so we can, actually, I'm gonna do it with a different color, so people are not gonna.
Variety in line.
That's open circuit? Excellent. Sure, yes. Okay. Yeah, so we have an open gate. Okay. So thank you. It's a switch.
It's open, sure. Open,
That's
sure.
one way to see it.
We're trying to find. This,
Yeah.
guys, it's right there. What's the short circuit current? It's the short circuit current, guys. What is it? It's not 1 amp. Look, so this determines the current on this mesh, no matter what. This means no matter what resistance is on this mesh, it's gonna be 1 amp going in that way. Well, we're measuring our short circuit current in this way, right?
Yes.
So PSC, that's gonna be -1 amp, yes. Does that make sense? Everybody following so far?
Yes.
Perfect. ISC is equal to -1 amp. Well, equals IR. Oh, look, guys, we did pass the sign convention right. R should be positive, right?
Right.
Validation. Right? So R should be 1 ohm, and I think we did it correct. Doesn't look like there are any errors. So this is,
Other than 2 divided by 1.
So
2 divided by 1 is 1.
it's 3. That's.
Yeah.
It's 2.
but the very last thing, I want to show you how to get to the R if you don't want to solve for voltage and current. So for the Thevenin, we can solve for V. We can solve for ISC. We can solve for REQ. But any of these two will get you the third one. So now that we know V and I, we can get to R. We could also have gotten the V and R, gotten the I. Does that make sense? Or I and R, and we could have gotten the V. Anyway, keep that in mind. That's what we did. We got the V and the I, we got to the R. But what I want to do is I'm going to show you how to get all three. So does it make sense how we got to the open circuit voltage, the short circuit current? We place infinite resistance across it for the voltage, and then we place just a bare wire across for the current. And it usually makes it very simple because there are some ways to simplify the circuit, basically.
Wait, how do we get the voltage?
The voltage,
Yeah.
we got it right here. We put air across that terminal right there. We did some node voltage analysis. And essentially, because these are equivalent right here, right? Like VB, let me see. VB and VC continue, right?
Okay.
All the way down. And so voltage of B,
We're just measuring the voltage drop across the two.
yeah,
Okay.
we're measuring it, yeah, exactly. And that's VB minus VC. But that's the open circuit voltage. Because we basically are just measuring, what is this if we place infinite resistance across? Does that make sense?
Yeah. Yeah.
It might take a second to cement.
So it doesn't matter like what else is happening,
What else is happening about, what do you mean by that?
like. Because we just worried about the 2 ohm resistor, because we're only worried about the drop across.
Yeah, so in this specific case, it's the first step. And yes, we're trying to do that. You will, on most of these circuits, have to like figure out what's happening around here and then get to that.
Okay.
But in this case, we knew what the current was across this.
Right.
And we knew what the resistance was. And so we knew that it's, where do I have it? We knew that it's like -2.
Okay.
If it was more vague, if we didn't have a current source, it'd be harder, but I would say if this is still a little weird, Fern, Ivan and I, those two, spent, I'm not gonna lie, like an hour and a half, and we did like 6 complicated Thevenin and Norton problems, and just went the whole way through. And there wasn't a single Thevenin and Norton problem on that test, which was a little annoying, but we knew it like the back of our hands by the end of it, so we could do it with our eyes closed. So do a couple of these. The physics behind it is a little weird, but once you do like a pretty good handful of circuits, you do a bunch of different methods, it starts to make more sense as to how you do. Yeah, also Sebastian and I are resources for you. So last thing, let's find that resistance. I'm gonna copy the circuit over here. Oops. Sorry about this.
Resistance is like voltages now.
Just the negative voltage. Not negative voltage. As some sonic conduction.
Yes, Dave. Please. That would mean it has negative resistance.
It implies power is being, sourced from somewhere else? Or is it that it's drawn power?
Big brain, it's like a dependence.
Maybe, yes. Power is always positive on a resistor because resistors are always absorbing power. If power is negative on a resistor, you're doing something wrong.
If the resistor is negative, what does it imply?
If the resistor is negative, it implies something weird's going on.
But it's possible.
It is not.
It is.
Negative resistor?
Negative resistor value.
I
It
don't,
implies something else.
it might. I have no clue though. I don't know anything about negative resistors.
Probably.
No, that's okay. It could be negative resistance.
Not in this class.
Oh, yeah, not this.
Not in ENA.
Yeah, sorry.
This is the ENA review.
Sorry.
Kevin.
Oh, wait, yeah.
So when we get rid of our sources, what does the voltage source turn into?
For sure, for sure.
Yeah.
For sure.
Short.
Yes, a wire, yes. We're shorting it why? Because that's what we do.
I'll show you. So
Is it because
we found,
because we don't care about like any of the current or voltage whenever we're finding resistance?
yes. Yeah, if we scroll up, it explains it here. To find that R, we deactivate all of the sources and then we bias it. And we figure out what the R is if we bias it. So in this case, this is what it looks like so far. What does a current source go to?
Open.
Open, sweet, incredible.
It says in the textbook, negative resistance implies that the circuit is supplying power.
Oh, okay.
Dependent source. That's facts. That's facts. Yeah, actually, that's facts. Got that. It's like a dependent source.
All right, guys,
All right.
Yeah.
what is the equivalent of this? Does anything happen on this side of things?
No.
No, exactly. So we can just get rid of it. We don't need it. Like a toxic friend.
Cut it off.
So it's 2 hours.
What?
Answer's 2 hours.
Yeah. RTH is 2. And what did we say? We said it was 2 over here. Well, after figuring
Well,
out
it's like 2 ways.
that 2 divided by 1 is 2.
Yes,
Yes. So yeah,
good math.
you don't know why what?
Yeah.
You
Why,
cut it
why the left side of the circuit goes away?
Oh,
Is it because it has like the one resistor connector?
yeah, this is going nowhere, right? We are, when we are looking for the equivalent resistance, it's like we place a battery across and this is now our source. So current is only flowing through here. Nothing can flow if there's nowhere to go, right?
Yeah, because then you can't go back.
Yeah, so it's essentially just like loose wires that go nowhere hanging off. If you put your finger right on this. Yeah,
That's an excellent. He's an A-Tech.
It is for everyone.
It's better than back here.
Yeah, did you have recording? So you think-
Fernando, where you going? You gotta talk to me.
No, I'm gonna walk around a bit. I mean, I have a meeting at 3, so I'll be right back.
dude. I dare you. Anyway, let me keep going. Does that make sense?
Wait, that time? Why is it? I thought there was nothing there.
Well, yes, but if you put your finger there, now it has somewhere to go.
Yeah.
So there's your lesson. Don't touch loose wires unless you want to have a surprise dance party. So,
That's possible.
yeah.
You want?
Okay. Yeah, we can do another Thevenin and Norton. Honestly, Thevenin and Norton are definitely tricky. Just because they're hard to think about. A lot of this is like the tools, when you get the tools down, you get the methods down, it's really easy, which is why I preach like do a million problems before the test, especially with what you're uncomfortable with. Start simple, do like 5 simple problems, do 5 complicated problems. You'll be fine.
Do you have those practice problems that you said you did?
Yeah, well, I have a textbook full of practice problems that I could send you guys.
That you bought.
Yeah. I bought them. Yeah. I bought the textbook.
If you do another question.
Yes.
Natural response?
You wanna talk about capacitors and inductors real quick?
Yeah, natural response.
Okay. My wrist, I'm holding this heavy.
Oh, yeah,
I
I
can't-
can take over natural response.
My arthritis is kicking in.
Can we take over natural response?
Table and just.
Oh, good. Oh, could I sit it on the table?
Yeah.
But I want to face you guys. Here, I'll do this. We'll
It's
conference.
getting down on one knee.
There's
Oh.
chairs.
Kevin, this is being recorded, so. I wonder if I can. Technical difficulties. Oh,
That's a keyboard.
yes.
That's clean.
I'm not gonna break her iPad. Here's
Yeah, really?
me shattering Allison's iPad. in order to-
That's $900.
Yeah.
He's
Sit down.
dead for me for life.
I am 20 years old. So,
Me too.
oh, sweet, look at that. Kevin's like 14.
Baby.
Okay, so capacitors and inductors. So what we were dealing with were completely linear circuits with time. It's not that easy with capacitors or inductors, sadly, but they do have really interesting properties. And if you know about those properties, it becomes very, very easy to. So for capacitors, the current is equal to, or it's proportional to, we'll say that, the change in voltage over the change in current. So that means we cannot change instantaneously the voltage.
It just comes up.
Probably for like the word problems and all that.
Yeah.
There's a lot of those.
So this might be on the test, but it's not gonna be like, it depends, when are you taking your test?
What's it?
What I say?
I don't think it's gonna
We
have.
had one where we're condensing finding the inductors equivalent, and then we also had a question about like what you should do with like inductors and like taking them out, like not unplugging them, like,
Shorting them,
yeah.
yes. Ooh, don't short an inductor. Or
The-
don't open an inductor. You can short an inductor. Don't short a capacitor.
Yeah.
Then
No
it's
short and saturated.
yes. Okay, and we'll see why
I don't.
just a second.
I'll take it.
Okay. Yeah, don't take that.
I'm scorched.
So, let's say our voltage changes instantly. Bam, that's our voltage. That's T equals 0.
So that's what we charge about. We apply voltage to the capacitor.
Well, yeah, but
Okay.
let's say in this case, the voltage across the capacitor jumps.
Okay.
Well, C or I is equal to, or we'll, again, just do proportional, so we don't have to worry about C right now. I is proportional to dV over dt. That's change in voltage over change in time, right? So, what happens when T equals 0? Anyone take a guess?
Slope is infinite.
Right?
It's yeah. It's on. Open switch, right? So
But in this case, if I is equal to, yeah, change in V over change in T, and change in V is equal to, let's say, 1, but it's immediately, so the change in T is like approaching 0. That means that I jumps to infinity.
that's right.
Does that make sense?
Yeah.
So in order to jump up, it, bam, flies all the way
It's
up.
basically a Dirac delta.
It's, yes. Very good. I don't know how many of y'all have run,
Dirac delta.
how many of y'all have run into Dirac delta? That's, you'll get there. It's a function that's 0 everywhere, and then in the very middle, it spikes to infinity. That's what happens here.
Voting class.
No, not this.
No, it's not in that, it's in statistics, if you're taking statistics, and then it is it's in signals and systems. Which, it looks weird and complicated, it's relatively simple, it's just different.
Yes.
So yeah, we don't want that. We don't want infinite current because that would set everything on fire pretty quickly, right?
Yeah.
And in practicality, if this were to happen, there's no infinite current, but it would jump to the tens of amps levels and go back down, which we don't want. So capacitor naturally resists fast change in voltage. What happens? So let's say we've got a battery. Capacitor is not charged up. This is step response. At T equals 0, it clicks on, the voltage starts. Well, what happens first, because it resists instant voltage change, right? So where does the voltage start if it resists voltage change?
0.
And eventually, it climbs up to whatever the voltage source is, right? Does that make sense? So, yeah. In fact, let's
Let's solve the DQ to see why it's exponential.
yeah, let's do a little bit of it. That's what it is.
Yes. Let's go.
Okay. And then equivalently. So does it make sense so far?
Yeah.
What's happening here? Okay. So it resists change in voltage, but to resist change in voltage, the capacitor does silly things to the current. All right. So basically, if it switches, there's no current across the capacitor for T is less than 0. But then the second the switch clicks on, the current is fully allowed through. So it's gonna jump. There we go. It's gonna jump right here. Right? Does that make sense? It's just some ion. And then, because the voltage across the capacitor is climbing to the source voltage, the current bounces back down. And it goes to 0. So think about this, think about the physics behind it. Step response is when, bam, it starts to get powered and it's like charging up. The voltage starts at 0 and raises. So essentially, when t equals 0, the second t equals 0, this is what it looks like. Right? Voltage is nothing across it. Current is just fully allowed through. But then over time, the capacitor's properties kick in and it becomes kind of short, where all the voltage is across it and no current is allowed through.
Yes.
Everyone follow so far?
Yes.
Yeah. Let's see. Oh, look, I even left space for myself.
For the DQ, right?
And for the different Q.
Yeah.
I'm not gonna do it.
Never seen someone so excited. That's what Harry Potter.
Are y'all doing e to the tau t stuff on this
No,
test?
we're not doing anything.
Okay, so I'm just gonna leave y'all with the qualitative, like the properties of it, and then we'll from there.
Yeah,
You know-
that's your exam too.
You wanna do all your DPQ, you do all your DPQ.
I know, yes.
So for step,
Wait till you said this. Back of the hand. Oh, so- Yes, I'm not. Don't 120 volts fluctuate.
we're gonna keep that in. And then natural response is when it's like this, but then the switch turns off. Wait,
So that's discharge.
that's discharge.
Yeah.
Here's what natural response.
So I discharge is part of natural. It's just like, sorry.
No, you good. Thank you. It's been a little while since I've done this. So.
Oh, so you're introducing a resistor? Oh, wait, that's a. I see. Oh,
Yeah.
okay, I see exactly. Oh, because you're shorting it with the. Yes, he's discharging it through the resistor. So you're
Yeah.
gonna charge it up.
So for t between negative infinity and 0, it looks like this. So basically, you can imagine it's been charging for a long time, right? In fact, these connect pretty well. Because if you look, the end behavior of these two are what this will look like, right? After a very, very long time. So it has infinite, or it's not infinite, it has the voltage of the source across it and no current. Does that make everyone following so far?
Yeah.
We say a capacitor is charged like this, because if you think about it, it's holding that voltage and it's like a little battery. It's a battery that'll go off and release that energy and then that's it. Does that make sense? Okay, so the second that switches over, t equals 0.
Isn't there a, isn't there an actual aspect? Like if you didn't have the resistor, would it naturally decay?
Yeah, it would. I like placing the resistor there.
Would that be short?
That would be shorting.
That'd be short.
Yeah.
Okay.
So the second the switch clicks over, it has that voltage, that source voltage across it, right? And so it carries the source voltage.
Yes.
T equals 0. Say the voltage. Well, the voltage has been here on that capacitor this whole time. But then the second it clicks over it, bam. Now, let's look at the voltage, or let's look at the current. This is the current across the resistor, but it's also just the current across the whole circuit. Well, the current the whole time has been 0. What happens when the switch clicks over immediately?
current will. That'll do the exponential.
It won't climb up. It won't climb back up because the current eventually, the voltage dissipates across the resistor, right?
Wait,
So-
oh wait, it'll look like this. Oh, so I see, okay, it's
Does
cause
that make sense?
it's gonna flow.
Spike up first and then get.
Yeah,
Exactly.
that's
So,
what it is. Yes.
and it's gonna spike up to VS over R.
Yeah.
And then carry back down.
I see.
It's like a little, yeah, it's like a little mini battery.
Oh, because
And then
your
it loses.
voltage is also changing.
Yeah. Because the voltage is declining. So independent voltage sources, we just assume that it's like that forever. Yes, ideal. That's right. Thank you. But capacitors are more like realistic batteries because they lose their stuff after a while. But yeah. And you said, what if we don't have a resistor here, basically?
No.
So we made a joke about shorting a capacitor earlier. Well, if R goes to 0, what happens to the I? Does that make sense?
Yeah.
What does it do?
Goes to
Yeah, you know the answer.
an infinity.
Yeah. I may have not heard you. I'm gonna put a little skull there.
That's that.
Okay, and then whenever you open the inductor, that could be longer.
Yes. So
This one makes point. I mean.
You could
Where's right? We built it up, right?
That's how I tried.
the way you can think about it too is a capacitor. I've got 10 minutes. I'm gonna have to go through them.
Let's go.
But when this ends, if y'all have any more questions, I'll talk about it too. A capacitor will place voltage, the same voltage, no matter resistance. So if it's a charged capacitor across some little r, or if it's a charged capacitor across some big R,
That's connected.
no matter what, the same voltage is going to be applied across.
Yeah.
And so what changes is the current, which means if you have a no resistance resistor, it's the same voltage is going to be there. So the current's going to spike, go way, way high. All right. So keep that in mind. Capacitors resist change in voltage. Inductors resist change in current. So here, if the current jumps up, then what's going to happen to that voltage?
Impulse.
Yeah.
Dirac delta.
Real quick. Yeah, and that's unrealistic. You cannot do that. So, when we're powering an inductor, the voltage, the current will start off very small and then rise to where it should be, right? In fact, we're gonna do this. That way, it makes more, it rises to that source current. Right? Everyone following sometimes?
Yeah.
Good.
Yeah.
And your professors are probably gonna give a better explanation of this.
So it's perfect. It's perfect.
I don't know.
That's the best explanation I'm getting.
Really? Okay, okay, good. Then, now current starts at 0. That means this is an effectively open circuit the second it starts, right? So what's the voltage?
0. Voltage,
No, we don't, I guess I didn't give y'all a value to talk about, right? Well, the voltage is at its highest. Whatever it is, it's at its highest and then it goes down to 0.
yes.
So you can think of this as, I'm just gonna put this right there. Just like how you can think of a capacitor as starting out as an open and then ending, or starting out as a short where it allows all current through and has no voltage. And then it transforms over time into an open where there's no current and all voltage. Inductors start out
I like versus.
as an open and then go to,
Be wrong to say that an inductor stores charge, that I mean, not the current.
no, that's exactly.
That's what they do?
Yeah, yes,
Okay.
it stores, so they both store energy.
Okay.
Capacitors store in terms of the electric field, but in ENA terms, it stores voltage.
Okay.
And then inductors store, well, they store magnetic flux field.
Which is.
In ENA terms, they store current. Yeah, but inductors are interesting, you'll see. Over time, it looks like this, and then, yeah, whatever current is across this, it's gonna be holding on to it, basically. Yeah, let's do a step response real quick.
Yeah.
Real quick step response. IJ. Sure. And the reason I'm not using a voltage source, by the way, is let's say there's a voltage source powering this. Well, eventually it's going to get to a voltage source equivalent, like powering what's basically an open wire, right? V equals I times R is going to 0. And so once again, I goes to infinity. And so it's 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 not good. It's not good for the soul, not good for the body. Yeah. Again, a lot of this is really like, a lot of this takes some time to think about. Yeah, so on all of my exams, I would do this. I would draw out what I think it looks like at first. And then what it looks like at the end. So let's do that step response. Voltage with time, when t equals 0 right here. The voltage is nothing at first, obviously, because there's nothing across this, right? So it starts out before time is 0, at 0, and then it jumps to whatever V max is, and bam, spikes right up there. And then because it's going to an open, or it's going to a short, it lowers down. Then let's look at the current.
Ever know what V max is?
If there was an R,
Okay.
then it would just be, yeah, it would just be IR. I think.
Here would use the time constant. Then at the 5th time constant, or the, never mind, sorry.
No, that's. Yeah, and there's also, you're also likely gonna see something like this. Switch down there. And then it starts out when you click it in, the light switch, it's gonna look like this. And so that R doesn't even matter at first, right?
Right.
Because there's no current going across it. So it starts at VS and then it declines to 0. And so we can also measure the VR. It's going to start at 0, right? Because all the voltage is across that inductor first. And then it shoots up to VS. Well, Kirchoff's voltage law, this is a fun little extra thing. Kirchoff's voltage law says VS is equal to VR plus VL, right? What if we add these two graphs up? It would be this plus this. It would just be VS.
Wow.
It's math. these circuits, they're not just crazy things, they make sense.
Wait, Gordon,
Yes,
I don't know if this is the right concept, but isn't when that first graph, when the equal, is that the resonant frequency?
which one?
When the two,
Where they
exponent curves?
intersect.
Yeah, where they intersect, is that the resonant frequency?
Not in this case,
Okay, okay.
because we're doing transient analysis.
That's right.
We're not even worrying about frequency in this
Okay.
case. You will get to a point where that,
We put inductors and capacitors together.
yes, but in this case, yeah. Oh, are we?
Are you almost done?
I'm almost done.
Okay.
Am I allowed to go a little bit longer?
You're good.
Okay,
Just tell me whenever you're ready.
we're gonna be a little quick about this then. So current, when it clicks on, starts out at 0. And then climbs up, right? Because it starts as open, infinite resistance and ends at no resistance. That makes sense for everyone? Clicking for everybody? Okay, so step. The voltage across the inductor with time shoots up, goes down. The current across the inductor is the current across the circuit. Is nothing and then goes up. Well, what about natural? What about that one, you ask? Oh my gosh, what's going on here? Well, let's hit them with a beautiful looking circuit.
Thanks.
It's
Just absolutely picturesque. I can put the ground in there. How about this? All right. Well, between negative infinity and 0 when it switches, we can assume that the current across the inductor has risen to IS. Does that make sense to everybody?
Yeah.
We can also assume that the voltage has gone to 0. But we don't really worry about the voltage here. Just because inductors store energy through current. But here's the thing. Oh my gosh, guys, this is what makes inductors interesting. The current direction is this, right?
Right.
So the second we switch over, we think of our R as biased this way, right?
Right.
But the current, because it resists change in current, the inductor is still pushing down, and so it's going in the reverse direction. So what's going to end up happening is when you switch that thing, the I across the circuit is 0 at first. It goes down, biasing it in the right way. And the voltage across the resistor wait, is that wrong? Okay. No, that's correct.
Yeah, because you start at negative voltage, then you go to
Wait.
Because we close the switch, isn't there a burst of polarity on the inductor? Wait, or not?
Like Faraday's law.
Yeah,
Faraday's law said.
that's the first question on the test.
Is it really?
Yeah. they were the-
my conductor really said that, dude? That's
Michael
great.
and Doctor are better than.
Describe Faraday's law. I was like, I don't know.
No, I think we need to use Fourier transform.
I think we need these for it.
Fourier transform is probably better.
You see, the voltage across R is 0 at first,
Mhm.
and then it jumps to whatever negative I, it jumps to negative IR, right?
Yeah.
And then it goes down. Notice in both cases, the capacitor and inductor store energy and then dissipate it. And you can see it's relatively quick depending on what it is. It's goes away. You'll learn more in the next unit about the time that it takes. There's a specific way that we time it out. And this also follows e to the negative t. All of this, it's some sort of function of e to the negative t. But again, this is just the qualitative data. You'll get to how to actually like measure it and calculate it later. But yeah, so that's it. Do you save this? And then we can.
It's saved.
Oh,
Yeah.
sweet. Gosh. How was it?
That's fireside.